All right, for our final example, let's take a look at a box initially at rest being pushed up an inclined plane with a constant force of 100 newtons in the direction of the incline. We're going to calculate the velocity of the box once it is 10 meters above the ground. So on my diagram, it would look like this. Okay, we're looking for the velocity of the box once it is 10 meters high above the ground. And I didn't mention this in the problem statement, but the angle of incline here is 30 degrees and the mass of the box is 5 kilograms. So you can just add that to the problem statement or the given information. Before you continue watching this video, I would like you to pause the video and attempt this problem on your own from start to finish. Once you're done, come on back to the video and see how I've solved it together. All right, now let's take a look at the different forms of energy the box has at the beginning when it is at rest and it is not really up the inclined plane at all yet. So because the box is at rest, we will not have any kinetic energy, no motion, no kinetic energy. And because we assume that wherever the box begins, it's at the bottom of the inclined plane, we're going to say there's no gravitational potential energy at the beginning either. So it's on the ground and it's not moving. So therefore, the box has no energy initially. And let's go ahead and explicitly define our system as well. Let's say it's the box and also the Earth so that we can talk about gravitational potential energy. Before I get to the system or the work being done on the system, let's go ahead and think about what kind of energies the box is going to have at the end by the time it's 10 meters above the ground. Well, it's going to be moving, so it's going to have kinetic energy. Let's just go ahead and say, I'm just going to say 2 bars of kinetic energy. We can refine the numbers later. So it's got 2 chunks of kinetic energy, and then it will also be some height above the ground, right? 10 meters above the ground. So let's just say it has, let's say 3 chunks of gravitational potential. Now, I'm not necessarily saying that it's going to have more potential than kinetic. I don't know at this point. I'm just guessing, and we'll see at the end how close my guess was. All right, now in this problem, we're not going to include the inclined plane as part of our system, so we're not going to have thermal energy. Instead, we're going to consider friction as an external force doing work on the system. We can also say that the coefficient of friction here is 0.3. That's something that you'll need to solve the problem. All right, so I have at the end 5 chunks of energy. I didn't have any at the beginning, right? So that means that in my system, right, there needs to be 5 bars of work being done on the system total. Well, I know that there are 2 external forces acting on this box, right? If I go ahead and draw a little force diagram here, you will see that. All right, so I've gone ahead and drawn a force diagram for the box being pushed here on the left side. And I'd like to go through each force right now and circle the external forces doing work on the box. This is a recommendation I have for you when solving problems. You might ask yourself, I don't know what forces are doing work. How do I determine that? Well, if you draw a force diagram and then circle all of the forces that are external or caused by things outside of your system and are in some degree related to the displacement of the box, then they're doing work on the box. So let's go through this. The applied force here, is that an external force? You bet it is. The person is not in our system, and it is being applied in the direction of our displacement, which will be up the hill. So we're going to say that one is going to do work for sure. So there will be work done by the applied force. The normal force and the gravitational force in the y direction, if you consider the displacement, I'll go ahead and draw my displacement vector as well. We'll say that's d, right, up the hill. Those are both 90 degrees to the displacement vector, so they will not contribute to any work being done on the system. Now, if I think about the x component of gravity, I may be tempted here to include that as work, but let's think about that. This is the force that the Earth exerts on the box. Is the Earth an external object? In other words, is the Earth outside of our system? No, it's not. The Earth is inside of our system. So because we included the Earth in our system, it can't do work on the system. That would be only for things that are external or outside of our system. doing work on the system. So gravity here will not be doing work. Instead, we're going to consider the gravitational potential energy of the box. Last thing is the force of friction. That's caused by the inclined plane, the surface of the inclined plane. And that is an external force, and it is opposite the displacement vector. So it is at least not perpendicular. So it will have some component there that does work. So we know we have two forces that do work. So I'm going to show two arrows. One of them will be going into my system. We'll go ahead and show that here. I'll use a different color this time. I'll use green. So I have an arrow going in, and let's just say that there are, let's see, I had 5 bars total at the end. So let's just say there's 1, 2, 3, 4, 5, 6 chunks. 6 chunks of work. So this is like a positive 6 there. And then that is the work done by the applied force. And then let's show some work being done that's negative. So we'll show some energy leaving the system. I'll show that in red. And so actually, I'll use a different color. Let's go ahead and use yellow for that one. So that'll be, let's see, 6 coming in. That must have just been then one chunk leaving our system. All right. And this is the work done by friction. And this is going to be negative, and this one will be a positive value. Okay. So I made sure that there were 6 coming in and 1 leaving because I said that there was 5 chunks of energy at the end. Again, this is all arbitrary. How you decide the quantities of the bars is totally up to you. All right, now that we have identified and analyzed our initial final energy states, our system, and any works being done on our system, we can write out our energy conservation equation. That will be equal to, so we'll have, say, 0 here, no energy at the beginning, plus the work done by the applied force, plus the work done by friction. Again, I'm adding them both later. The work done by friction itself will be negative, so I'm not going to subtract it. That would end up giving me a double negative. So just add all of the works together and then worry about the sign later when you plug in the value. So initial energy of 0 plus all of the works done on that system will be equal to some kinetic energy at position B and then the gravitational potential energy at position B. And this is our conservation equation. All right, so the first thing I'm going to do, I'm looking for velocity. So I'm going to expand both the kinetic energy term and all of the rest of my terms as well because I don't really have any of the works or the potential energy directly. I'm going to expand those into their individual components. All right, I've gone ahead and expanded each of my terms here. And I've specifically not put anything inside the cosine values for the applied force work and the frictional force work. Let's take a moment to think about that. The incline here is 30 degrees, but it's important to keep in mind, look at the direction of the applied force, right? The applied force is in this direction. Well, which direction is the displacement of the box? In other words, which direction is the box traveling in at this moment in time? Up the hill, right? This is my displacement vector if I continue like that. So if you consider the applied force in the direction of the displacement vector, then the angle here, theta, is going to be 0. There's no difference between those two vectors in terms of direction. So the angle will be 0, not 30 degrees. Again, it's because we're pushing, that applied force is applied up in the direction of the inclined plane. If it were applied flat, then you would have to consider the fact that the box is moving in a different direction. But in this case, the applied force is parallel to the inclined plane itself. So theta will be 0. Now, friction, like you might have imagined, is going to point opposite that motion, directly opposite. So theta there would be, so this is theta. Theta is 180 degrees here, directly opposite 180 degrees. Okay. All right, now since I'm solving for the final velocity, I'm going to rearrange for that algebraically first before I plug in any other values. Before continuing to watch, please pause the video and take a moment to see if you can rearrange this equation for VB before proceeding. If I rearrange this equation for the velocity, it will look like this. I've gone ahead and shown my steps in algebra in blue. And remember, cosine of 0 is 1, and cosine of 180 is -1, and that's where the negative in front of the force of friction came from. I went ahead and multiplied both sides by 2. I divided by the mass, and then took the square root of both sides to get an expression for VB in terms of the applied force, displacement, frictional force, mass, acceleration due to gravity g, and height of the box. Now I have all my values except for the displacement, but I can get that with just a little bit of trig. If I draw the triangle that represents the inclined plane, I would show you that this is 30 degrees, right? 30 degrees. And I'm looking for the moment when the box is a height of 10 meters, right, in the y direction above the ground. And so if I want to solve for how far up the hill this actual displacement was, well, that's just the hypotenuse of this triangle, right? So I can say that sine of 30 degrees is going to be equal to opposite over hypotenuse, right? So at the moment, the box is 10 meters vertically, a vertical height above the ground. Then if d is the hypotenuse of that triangle, I can use sine to relate d to that height. And that means that the displacement is going to be equal to, I'll multiply both sides by d and then divide by sine 30, 10 divided by sine 30 degrees. But I know that sine of 30 degrees is just 1/2. So 10 divided by 1/2, that's the same thing as saying 10 times 2, which is 20. All right, so my displacement there is 20. And I'm almost done. I actually don't have the force of friction either explicitly, but it's fortunately not too difficult to obtain. I know that because there are no forces acting on the box in the perpendicular direction of the inclined plane. So to illustrate that, let's take a look at a force diagram really quickly. This is the same force diagram we've drawn for inclined planes as before. So I have that applied force up the hill. I have my frictional force down the hill. This is the y component, right? FGY. And this is my normal force. And then I can also show that, let's see, FGX here. So I'd like to remember that in this scenario, because the box is not accelerating in this direction, right? This is our new y direction. That means the normal force here is equal to the y component of gravity. So I would say that Fn is equal to FGY, which if you remember the triangle that we drew, so if I'll draw on this diagram here. If I draw this triangle, right, this is my FGY, and this is my, let's see, my FG here. So this happens to be theta as well. So FGY is equal to mg, which is just FG, times cosine of the angle of incline, 30 degrees. If you need to rewatch the video on inclined planes to jog your memory on that one, please take a look at that again. But this is the same way we solved for the normal force and force of gravity's components as before. So I know that the frictional force in this case will just be that normal force mg times cosine theta times mu, which in this problem, again, we're going to assume that mu is 0.3. That'll be the coefficient of kinetic friction. So I can say, I'll write that down here, that my force of friction, kinetic, is going to be equal to, this is just the same thing as force of friction, right? Either way is fine, is equal to mg times cosine of 30 degrees times mu. And now I know all my values. I can plug them all in to this expression that I've obtained here. And when I do, I'll get that my velocity is equal to 22.4 meters per second. All right, so this was a complex problem that involved a lot of different things. It involved two works being done, right? Work by the applied force and work done by friction, one positive, one being negative. It involved both kinetic and gravitational potential energy, and it also involved physics involving inclined planes. This is a great review of a lot of the concepts we've talked about in this class so far. So please review this problem and make sure that you can solve this problem again on your own. I would also encourage you to try solving this problem using Newton's second law and kinematics only as an alternate approach and compare that with this approach using energy and work. This concludes our series of videos on conservation of energy. Please take a look at Canvas for some additional practice problems to develop this skill.